a lot of times, that just also is code words for you probably won't get to use the calculator on a test. But let me show you here. If you go to the calculator and you hit the button that says apps, there's one on there that says conics. And then that way it'll show you the different format. There's 4 conics you look at. We look at, LeBron, does yours have that? Because I don't remember if yours had the updated software on it. Hit the button that says apps. It's still loaded up. The one that says conics. Well, I'll just work on it. So if you look on that word, well, mine's still loaded up too. There's a button that says apps, and you can hit the thing that says conics, and it'll show you 4 options. You have hyperbolas, parabolas, circles, and ellipses. Now, these 4 different conic formulas and whatnot, variances within them, I'm never going to make you memorize them. Even if you don't have your calculator, what I do is that I take a screenshot of them, and it will look like this. And it has something on there right away. This is basically what it shows you. If you look at it, you'll see how an ellipse, depending upon where the a squared is placed, it's stretched left and right or stretched vertically. And what we're going to do is start talking about what do those a values mean? What do those b values mean? What do they represent in the function, or not function, in these formulas and stuff themselves as you graph them? Yeah. Hyperbola. A hyperbola is a double-sided parabola, excuse me. A hyperbola is a set of values that has a vertex in the middle, a center, vertices here, co-vertices here, that create this rectangular box that have slant asymptotes. That's what a hyperbola does. They're mirrored images, they're mirrored parabolas, basically. Yeah. These, they look awful, but once you get the idea of what the values mean, as far as what we call these A's and B's, and eventually we start talking about the C value as well, once we learn the relationship between the values, it's very easy to work with, okay? They're very, very easy to work with, all right? Ellipse, these are the hyperbolas, and hyperbolas can go up and down, or they can go left and right. Well, you get the idea, but same things with, we don't deal with them in terms of slant hyperbolas. That's a pre-calc thing. I think we did. But yeah, there's little stuff like that. So let's look at this thing called a parabola. What I want to do is talk about a regular old boring x squared parabola. And what we've done in the past is that we've always had this x squared equals y, or y equals x squared, where the value of a determined whether it was up like a cup or down like a frown. If it was up like a cup, we knew that if the a value was positive. If it was down like a frown, the a value was negative. So what we do is, when we would graph this, this one would be placed at the origin, and it would have looked something like that. Well, when we start talking about these in terms of conic sections, as opposed to just graphing them with axis of symmetry and getting a couple symmetric twins, what we do is a little bit different. I'm not going to worry as so much about point values on the curve, but what we're going to do is look at what's called a focus, a vertex, and what's called its directrix. Parabolas, whether they're up like a cup, down like a frown, left or right, they all have these 3 values. Vertex. In this case, everything today is going to be placed at the origin. So vertex for everything is going to be 0, 0. Yes, ma'am?
Is the directrix, is that the point?
I'm getting to it. I'm going to explain all those parts here. The focus, the easiest thing to think about is the focus. a parabola will always open up to its focus because this curve is looking at something. Think about eyeglasses. Your eyeglasses help you focus from the back of your eye through your eyeball to some point. The curve of this adjusts where the focus is. If you look at the curve of your glasses, if you move your glasses out a little bit further, they become a little less focused. If you push them in, they're a little less focused. You move them to the left or the right of that value, they don't focus at that one spot. I mean, roughly, but you get the idea. That's what these things do. Glasses are made up of parabolas. Those sound bubbles, when you see them on the NFL sidelines, things like the hyperbolic sound thingies, I forget what they're called.
Boomsticks?
Yes, whatever. Where they have the mics in them, where they're the parabola. It's a cone of shame like your dog wears.
You are wearing no, that's not what I was talking about. I know you're
But it's the idea that there's a certain value of this focus piece that picks up the sound waves bouncing off the sides of the curve of the cone, or the parabola. The parabolic mic, I think that's, yeah, you just said that, didn't you? Yeah. You said,
I said boomsticks.
oh.
That's something else.
Yeah, I'm thinking the parabolic style one. But the idea is that this focus value moves depending upon how open or how narrow your parabola is. This directrix keeps it balanced going upward. If it's going up, the direction is behind it. So let me show you what happens with this. If the directrix, or excuse me, if the vertex is and it's opening upwards, the focus is upwards. If it's down, the focus is below it, and where's the directrix? It's above it. They're always going to be opposite each other. If it happens to open to the right, notice the directrix is to the left. And if it's to the left, the directrix is to the right. Now what happens then is that if you have a horizontal line, your directrix is, when we draw that little dotted line in, it's kind of like an asymptote that's really not there, but it is there. It's not technically an asymptote.
What is that?
Oh, an asymptote. Do you guys know what an asymptote is?
No.
Jeez, I didn't know that.
That's
Okay.
the same, no problem.
What can't x be? -1. If x can't equal -1, because then you would be dividing by 0. So in a graph like this, you would have at -1 an asymptote. As it approaches it, it gets infinitely closer, but it never reaches it. It's like the idea, I'm not touching you, I'm not touching you, I'm not touching you, I'm not touching you. It is, but it's the same basic idea. If you look at it as 1 over x, if it's 1 over x, and you're graphing that, if x is 1, it's a half. Here's 1, 1, half, and then it'd be 2, and then it's just getting closer and closer and closer. But it's never going to be 0, okay? Because there's an asymptote, because it can't be 0. And then it mirrors itself going back the other way. That's what asymptotes are. Does that make sense? A lot of times. We're not to the asymptote yet, because this directrix is just an imaginary line that from the distance that we talk about from the focus to, from the focus to the point on a curve is going to be the same distance to here. Now let me say this is not drawn to scale, so you can yell at me later. The distances will be equal as they go out, okay? If it was drawn perfectly correctly, any point on a curve is equidistant to the focus and the directrix. That's all that means, okay? That's all that means. Yes, ma'am?
So it's like the dot on the parabola to the directrix is converted to the focus,
Yeah.
right? All right.
Yeah, that's all. So what's going to happen is that we're going to have x squared parabolas and y squared parabolas. So we have a couple of rules to look at them. Now, don't write all of this out. In other words, let's do this. Whenever we have an x squared parabola, we have this generic equation. What's that? This book, I'm going to use a mixture of the old book and new book this week. For our purposes today, I'm going to utilize old book material because the new book uses a different formula that is not given to you on your calculator. It's a variant of this. I just don't like it, to be honest with you, because it's just ugly looking. What this is going to allow us to be able to do is that we're always going to be able to work with a very simple curve. If my center is here, this distance from the focus to the vertex is always going to be this value, p. P is the distance from vertex, very bad M, to focus. If it's opening upward, that p-value is positive. If it's opening downward, the p-value is negative. Now the opposite of p,
That's only if it starts
it will always be. This distance from your vertex to focus will always be a p-value. Because I had this example up here a second ago. If I look at this one, if my vertex is placed at 1, 4, and my focus is at 1, negative 2, that means my vertex is looking at my focus, so it's opening downward. The distance from here to here, I move down negative 6.
I get it now.
And that's where I'm getting this p-value from. All right. Other thing people started asking me a lot about second hour is why am I drawing these distance markers with little curves? The reason that I do that is because all of our parabolas like this, there's always this axis of symmetry, and if I'm just counting on that, it's tough to see. That's why I draw this little curve coming out of it. And I know that these two distances are going to be congruent to one another. But in this case, the directrix then is going to be, well, what's the equation of every line that's horizontal? Y equals something. So in this case, my directrix is always going to be y equals, well, here it's just going to be the opposite of p. Now, eventually, when we start moving things around in space, it's not so bad when it's vertical. All we had to do was adjust from the vertex, just counted up 6, and that's why I had it at y equals 10, as opposed to, because we had to add to the h, or excuse me, we added to the k value here. And we'll talk about the shifted stuff probably next week, okay? Once we start laying it all out there and understanding what all these little bits and pieces mean, it's very, very easy to work with, okay? You have to believe me, okay? Now, if it was a y squared, move this up a little bit here. If it's a y squared parabola, well, I'll do a positive one to start with. What changes with the directrix? What's the equation of the directrix for a y squared? It's going to be x equals something because it's a vertical line. One thing I want you to see is that this directrix, if it could, it would go through the parabola at 2 points. It would touch it in 2 spots. See how if I moved this one up, it would have touched it in 2 spots? If I moved this one over, oops, well, if I moved it over, it would have hit it in 2 spots as well. So the directrix would always be able to touch 2 of them. Vertical lines are x equals. So the same deal here. Vertex to focus is p. Vertex to directrix is opposite of p. So we're going to look at equations that look different from what we did with x squared minus 4x plus 6 instead of trying to factor all that, find zeros, get your axis of symmetry and plot, what we're gonna do is we're gonna look at ones that have it in terms of y squared equals negative 16x. And we're gonna have to figure out how to graph that. How do we find the focus? How do we find the directrix? Because last time I checked, there's no y squared button on your calculator. There's no get x by itself and solve. So we need to look at it in terms of these generics. So what we're going to utilize here a ton is these two very basic ideas. Oops. Next page. Let's see. So if it's an x squared parabola, it's either going to be up or down. If it's y squared, it's going to be right or left. And it just depends on that value of p. It's positive or negative. Positives are either up or to the right, just like you would count normally. Negatives would be left or down, just like you would count normally on a graph. Okay? Either one, that's how we set those things through. Let me show you an example of how you can start with a very simple equation, graph it, and write it all out. And I'll do it on the whiteboard, then I'll put it on the smartboard so we can all see it at the same time. One marker. I had 6 some earlier.
One over here.
Yeah. Let's say we have this. X equals negative 1/6 y squared. Let me do this. If I have x equals negative 1/6 y squared. First things first. Is it an x squared or a y squared parabola? Y squared. So that means it's either going to open up to the left or it's going to open up to the right. Now, we know it's a y squared parabola, which means we're going to get it in the form y squared equals 4px. Which means, what do you need to get by itself? Y. Not all of y, just y squared. Okay? I'm not trying to root anything here. So I want to get y squared by itself. So, in this case here, when I read it like this, it's the same thing as saying negative 1/6 y squared is x. How do I move that negative 1/6? Multiply. It's negative 1/6 times y squared, so let's multiply everything by negative 6. Okay? You weren't wrong by saying divide by negative 1/6, but we're going to flip reciprocals and it's just a little bit cleaner to work with. Okay? What's that? It's the generic formula. There's a reason there's a 4 there. There's always with parabolas. There's always this scale. I don't want to say scale factor. There's a factor of 4 that's thrown in there because it's like one of those things how you stumble across it always works. There's a 4 there. I can show you the long-winded version of it, or just that there's a 4 there. What's that? Yes, it really is 6 o'clock. Go to bed. So that means that we're going to get y squared equals negative 6x. Which means then, this negative 6 is playing the role of what in the generic equation? Not just p, but 4p. The p value is multiplied into it to equal that negative 6. We need to figure out what that value is. So what this happens is, this negative 6 is playing the role of 4p. So all we do then is set those two equal to each other to solve for p. Negative 1.5. Our p value here is negative 1.5. We know now that it's a y squared parabola. It's negative. So what direction is it going to open? That way, correct. It's going to open to the left. So we know that there's no shift here. So our origin is going to be our vertex. It's going to open to the left. I know that yes, sir.
Did you see the way it opens just from the negative 1/6?
Yes. Yeah. Absolutely. The only reason why we use the rest of it to go to the p-value so that we can count how far out to place the focus and how far back to put the directrix. That's all. Yeah.
How do you know that it used to go left?
Is it positive or negative? Negatives go left. We know it's a y squared, so y squared is either going to go left or it's going to go right. If it winds up being negative, it has to go left. If it's positive, we go to the right.
Where did the x value? Because you put negative 6 equals 14.
It's still there, but what's happening is that in the generic equation, we have this y squared equals 4p times x. In our equation that we started with, we have negative 6 times x. That just means that negative 6 is being played by the role of 4p.
Oh, okay.
So we're just trying to figure out what the multiplier of p gave us negative 6. Negative 3 halves. Okay.
So you always like put 4 as the denominator?
That's how you get p by itself.
You always do.
You always get p by yourself, p by itself that way. Yes, 1/4 times whatever that value in x is will equal p. So that means, let me move this up then. 1, 2, there's my focus. 1, 2, there's my directors. The focus is at negative 3 halves, comma, 0. And the directrix is at x equals 3 halves. That's it. It's very procedural. It's very procedural. The idea is understanding in a parabola, you're going to have some value of p. P will always give you the distance from your center, your vertex, to your focus. If p is negative, you're going to go left, or you're going to go down, depending if it's either x squared or y squared. Okay? And that's how we walk ourselves through. I'm assuming you'd like to do another one. Maybe. No, no. Let's say we have, yes, okay. So x squared over negative 36 is y. Which means it's in, we know right off the bat, it's going to be an x squared parabola. Why? Because there's an x squared. Kind of helpful, okay? So we know we're going to have an x squared parabola, which is going to equal 4py. Which means I want to isolate the x squared. How do you undo divide by the negative 36? Multiply by negative 36. So we get x squared is negative 36y. Which means negative 36 is playing the role of 4p, not p, 4p. It's playing the role of 4p. So negative 36 has to equal 4p, which means negative 9 is p. X squared, negative p value, up or down? Down, very good. Okay. We know then our centered, where's the vertex? The origin. What's the x, which?
Why is that the origin?
Everything today starts at the origin.
Today?
Well, like, what equation makes that?
Today.
So we get to origin.
There'll be an H in there. So we know that this has to open downward because it's negative, but our focus is negative 9. It's down 9 spots. What's the ordered pair for that focus? 0, negative 9. So a focus at at 0, -9. Directrix then is above it. You're not trying to scale, thank you. What's the equation of the focus? Or, not the focus, the directrix here? Ah, that's an ordered pair. It's a y equals 9. So the directrix, that 36 is there to kind of, it's morphed from 4p. 4 times what got us to -36. That p value is going to let us figure that out. That's where this is coming from. Let's try another one. Let's say you have vertex. Oh, I don't. Write the equation in the standard form with the vertex at 0, 0, and a directrix of y equals 2. So, directrix. Directrix are always either it's a horizontal line or some vertical line. This one is a what kind? It's horizontal. You're on the right track. We know that it has to be at the origin because it said so. It has to be a directrix at y equals 2. Very good. This distance is whatever from the vertex to directrix will always be the opposite of p. So that means the other one had to go this way. Since the focus went downward, the p-value is negative. Is this going to be an x squared or a y squared? It's going to be an x squared because it has to do this because this is going left and right, which means the parabolas drop left and right. It's the easy way to remember it. P-value is -2, which means you're using an x squared equals 4py. If p is -2, what's my equation? What is it?
X squared equals
Yeah. Yeah, exactly. And Danny, you were just saying, well, how do I know it's an x squared? Okay, I know it's x squared because the directrix goes left to right. The directrix, if it could, it would like to punch both tails of the parabola. So the directrix going left to right would be able to hit this on both sides. If the directrix went if it went left and right and the parabola only went to the left and like this, it would only hit it in one spot. It wouldn't be very happy. It wants to hit both of them. What's that? So that's because if you're given a y equals for your directrix, it has to be an x squared for those.
So like if you were getting, if it was like x equals to y squared then?
Yes. Yes. Your directrix is always going to be the opposite of whatever the squared is. Does that make sense?
Yeah.
Yes, ma'am.
But why wouldn't you just put y into the equation then too?
I haven't gotten that far yet.
Okay.
I was just asking, since my p-value here is -2, my final step is just to fill in the blanks. And I get x squared equals -8y. And then I'm done.
Well, why wouldn't you just put in 2 for y? Because y is equal to 2.
It's saying y on
So
the
it's
side.
essentially what we just found.
Yeah, it's saying this is the directrix is this. We need to use this directrix to come up with the equation that has that directrix.
So at the end of this, what we need is either x squared equals something y or y squared equals something x.
Perfect.
Okay, then I can see that.
Sir?
Okay, why would you divide -8 to get to just y by itself?
The standard form that we're going to be using for these is written with the x squared alone on one side, or y squared alone on one side. You want to go to, oh, that's just y equals -1/8 x squared, because you can put that in the calculator. And which is fine, it's the same exact graph. In conic stuff, we use a little bit different nomenclature to write these things out. It's just another way to represent it, okay? It's just another way of doing it. So what we'll be able to do then, real soon, is say if the vertex is at 2, -3, and your focus is at 5, -3, you're going to be able to tell which direction it opens. How, you may ask? You plot it. Vertex 2, -3, which quadrant is that? Okay, you don't remember the quadrants, I get it. 1, 2, 3, 4.
Oh, I got 4.
Yeah, but you weren't sure about it. There's that one. If that's the vertex, if the focus then is at 5, -3, what direction does it open?
To the right.
It opens to the right. Is this an x squared or a y squared? It's a y squared. It has to do this. It's going to be a y squared. How far apart is that? 3. So you have a p-value equal to 3. Now, you don't know how to do this with the shift yet, but it's the same style. If you look at the generic form of the parabola in your calculator, the calculator has it in terms of the shifted already. X minus h quantity squared equals 4p y minus k. And then you flip it around for the other side. Okay? We'll get to that. But it's just a matter of moving it from the origin, moving it from 0, 0. LeBlanc, you look like you're really mad at me right now. Okay. It's just her face? Gotcha. Let's do one. Go back to what?
Is there a homework place and it's like safety in
Do you need to like write that in?
No, we don't know how yet. I'm not going to show you yet.
Yeah, like you said, it was always in the origin.
I know, but I'm just saying that the only thing that's going to change,
Yeah.
the only thing that's going to change is this.
Yeah, that's the only
What's your h and your k for that? What's your vertex? My vertex is 2 and -3, so here's your h, and there's your k. That's the only thing that's changing. Because where's your vertex today? 0, 0. Y minus 0 quantity squared is just y squared. X minus 0 is just x. That's all it is. That's the only thing that's going to change. Okay, fine. You can memorize it. Merry Christmas. Anybody else want to just memorize it?
Who's memorizing? What are we memorizing?
Bozo is.
Okay, that's fine.
Oh, younger Bozo. Shorter Bozo.
Which one's mine?
Nick. He's trying to act cool. I didn't say he wasn't. I was just kind of giving him the more of the he's trying. Every other odd, it works out to be 15 problems, guys. Okay? All right.
Is this old book or new book?
This is old book. Thank you for reminding me. I threw it on there. This is section 10.2. I uploaded to the website earlier today all of the chapter 10 stuff that we would use out of the old book, but I would like to try to use some of the new book as well, kind of mix it in, because they do have the Math Excel stuff. Should all be up and running, and they have some really good problems that I can put in there to like mix all this stuff together. So we're going to utilize a little bit of mixture of both old book and new book, so we just got to make sure we keep up on which one it is. So thank you for taking it, and we'll go from there. All of this stuff is today, guys, is what direction is it opening? Where's the focus? Where's the directrix? Things like that. Yes, sir. Not today. I know I started to put an assignment on there, but then I realized that they're using the different equations for the parabola, and I did not like it. After I looked at it again, they use it as a fraction. They count everything in terms of c values. I don't want to mess up that c value from what it's going to be with ellipses and hyperbolas. They're different, so that's why I don't talk about it. Okay? Yeah? You want me to do another one, or are we all right?
We're good.
What's that? Yeah, everything tucked in. Whatever, please still allow people to have to take it. Swing in different stuff. Seem very flexible. Very flexible. Yeah, come in the morning. Oh, you can
Do it.
Emergency man.
What's up?
Kind of parts of the house.
Top shelf, you're not gonna cut your hair, are you? That'd be weird. She said you're holding her hair. You got scissors? Yes! Let me get them for you.
You have to I can
You slice.
One on here.